Hello and welcome to CircuitShepherd. In this video, we will define target values in the frequency domain. We'll show how to design basic RC low-pass filters and use this knowledge to provide our voltage divider and non-inverting operational amplifier circuit, which we have done in the previous videos, with a well-defined bandwidth limit. So let's build a basic RC low-pass circuit with a voltage source as input and a voltmeter to define the output. For better oversight, we place a Bode plot to visualize the transfer function in the frequency domain. In order to measure the AC transfer function at specific frequencies and get a cursor in the Bode plot, let's change the mode of the voltmeter to AC and define the same input as in the plot. To view the corresponding cursor, we bring up the Pinchable Plot by selecting the thumbnail plot, activating the pin button, and selecting the voltmeter again. Change the measurement frequency to read out any point in the Bode plot. Now we want CircuitShepherd to automatically dimension the circuit to get the corner frequency of the RC low-pass to the cursor position at 20 kHz. So we set a phase target of -45 degrees as design goal and give CircuitShepherd a sufficient degree of freedom by designating at least one part as auto. Once the circuit is set up, the corner frequency can be freely changed, just by changing the measurement frequency of the voltmeter. To minimize errors caused by auto part value discretization, we can provide CircuitShepherd an additional degree of freedom by also specifying the resistor as an auto part. A limited resistance range of 1 decade is sufficient to provide a maximum fineness. Okay, so now we'll use our newly gained filter design skills to provide the voltage divider with a bandwidth limit. Let's drop in a capacitor and add a Bode plot. To get a cursor in the Bode plot, we could simply wire a second voltmeter with AC mode setup to the output. However, CircuitShepherd provides a more convenient way to achieve this by allowing us to copy an already wired meter as an alias. Alias meters work as normal meters with the exception that they are not explicitly wired. Instead, they implicitly adopt the wiring of their master meter, which is the one they are copied from. Reference designators of alias meters are always prefixed by the one of their master. Again, the corner frequency is defined by setting a -45 degrees phase target and designating the capacitor as auto part. For the final, we'll also provide the non-inverting opamp circuit with a bandwidth limit. As before, drop in a capacitor, add a Bode plot, copy as alias, set up AC mode. However, since the circuit has a more complex AC behavior, let's take a closer look at the Bode plot before we set up any AC design target. For low-frequency signals, the AC gain simply equals the DC gain of 3, which is about 9.5 decibels. In this case, the capacitor can simply be thought of as an open circuit. Open circuits don't cause phase shifts, so the phase is 0. Once the frequency rises, the capacitor starts reducing the effective impedance of the R1 branch, thus lowering the gain and also shifting the phase. If the frequency is high enough, the impedance of C1 is so low that it can be thought of as an ideal short circuit, which causes a gain of 1 or 0 dB. Short circuits don't cause phase shifts, so the phase has to rise to 0 degrees again. For very high frequencies, there is a corner frequency, which is primarily determined by the gain bandwidth product of the opamp. Therefore, with the capacitor value, we can only influence the position of the 9.5 to 0 dB drop. Note that it doesn't make sense to set a -45 degrees phase as design target as we did in the previous circuits, since the phase does not cross -45 degrees in the range of interest. Also, simply setting a higher phase target is unfavorable since it would be ambiguous. Therefore, we need to directly set a gain target. Once set up, the position of the gain drop can be changed freely. Before we finish, one last hint. AC gain targets often have the disadvantage that they have to be readjusted if you change DC-based design targets, so it's recommended to prefer phase targets if possible. All right, we've learned how to define design targets in the AC domain and provided well-defined bandwidth limits to some basic circuits. Stay tuned for more in the next videos. Thanks for watching. See you later.